Good morning, everybody. Today I'll be teaching hydraulic jet pump. In hydraulic jet pump, we have one nozzle, we have diffuser, we have mixing chamber. Then we are trying to create low pressure, which low pressure will be sucking the high pressure fluid from the low pressure will be created, and that low pressure will be sucking the wellbore fluid. How this Venturi or this jet pump work? First, I will explain using the Venturi meter principle. If you have gone through your fluid machinery laboratory, there you may have done some experiment related to pressure gauge, manometer, Venturi meter. So I'll try to explain a little bit based on that Venturi meter principle how this jet pump will be working. Okay, in a laboratory experiment, normally there will be some system like this. This one like this. Okay, so if pressure 1, okay, this is 1, this is 2, okay, this is pressure 1, flow rate Q1, velocity V1, you have area A1, here I can say area A2, pressure P2, velocity V2, flow rate Q2, maybe rho 1, maybe rho 2, okay, mass flow rate maybe M1, this is M2 dot. Okay, now fluid will be flowing, it will create stream like this. Okay, fluid likes to travel through straight path. If it is having any restriction or any obstacle, then fluid will get difficulty to pass through that path. Okay, when it is having difficulty, it will get lots of losses. Here also in this Venturi meter system or the restricted system, fluid will try to create streamline, smooth path. Okay, so fluid will be try to create smooth path, streamlined. Okay, and you can see how this restriction is changing this fluid streamlines. Because of this streamline change, actually this section 2 pressure will be dropped. Okay, so P1 must be higher than P2, and flow rate Q1, Q2. What will happen to the flow rate? If it is liquid, incompressible fluid, we can assume that flow rate is not changing, because mass conservation equation you can remember. So there M dot equals Q rho Q, right? So rho 1 Q1 equals rho 2 Q2, and in this case density not changing, so our flow rate also will not change. Okay, so Q is not changing. Okay, because you are pumping in our wellbore, you are pumping hydraulic fluid, water or oil, so that water oil we can assume incompressible. Okay, for this specific application. If it is compressible, then case may be a little bit different, but for this case we are assuming purely liquid, and flow rate is not changing. But what about velocity? Velocity is Q by A. So flow rate or Q is not changing, Q is flow rate. Okay, flow rate is not changing, but area is changing. You see, section A is larger diameter, section 2 is smaller diameter, so area changing. That means Q okay, so formula will be like this: Q by A1 V1, V2 equals Q by A2. So area changing, flow rate not changing, so velocity changing. So whenever solving Venturi meter or jet pump related problem, where velocity changing, your flow rate not changing. And in this type of problem, normally we assume that there is no energy loss because of heat transfer or frictional pressure drop. If you can include that one, then that will create more complex problem, but we are assuming there is no energy transfer. So mass conservation, energy conservation rule will be applied. And this Venturi meter, we are using Bernoulli's principle. Bernoulli's principle, you can remember Bernoulli's principle: P by rho g plus V square by 2g plus Z equals constant, right? constant may have some more terms, maybe frictional terms or energy transfer term, but this is generalized Bernoulli equation. This is energy equation. Okay, energy equation means energy must be conserved. So this equation says energy is conserved, and here mass conservation equation I am saying. So mass conservation, energy conservation done. Okay, velocity will not be conserved, right, because of area changing. So Q by A, velocity changing. Now how this pressure is becoming different. Now section 1 pressure is P1, and you see the Bernoulli equation. I'll be writing same way, rho g plus V1 square by 2g equals P2 by rho g, because g and rho not changing, g cannot change anyway, rho also not changing, we are assuming, plus V1 square by 2g, and we are assuming other terms are not there, for example because of height, h term, or frictional pressure drop, or any other energy transfer term not there. So if you can simplify this one, it will be like this: P1 minus P2 divided by rho g equals V2, it should be V2 square minus V1 square by 2g. Okay, now from here again we can write P1 minus P2 equals G cancelled, so rho by 2 V2 square minus V1 square. Okay, so we got one formula how this pressure and velocity related to area. So when area changing, velocity changing, so pressure also changing. Now theoretical flow rate. So theoretical flow rate Q, V equals Q, right, V equals Q. Okay, now you can see you will rho by 2, so Q V2, you can say V2 equals Q by A2 square minus V Q by A1 square. Okay, we got rho Q by 2 Q square, actually 1 by A2 square minus 1 by A1 square. We got this one. Okay, now if I write Q equals will be root over 2 by rho P1 minus P2 divided by 1 by A1 square minus 1 by A2 square. I think one sign issue is coming here. V2 by V1, P1 minus P2, V2 minus V1. I think this is correct. Okay, now this is theoretical flow rate. This is theoretical flow rate. Okay, now if I have if I do experiment, then flow rate will change actually, because there will be some losses will come, so the coefficient of discharge will be coming. Okay, so experimental flow rate, or practically how much flow rate we get. Experimental, if we do experiment, then experimental flow rate will be Q experimental equals Q, I can write Q theoretical, QTH, okay, instead of only Q, QTH into CD. Okay, CD is called coefficient of discharge. Okay, so what is coefficient of discharge? Coefficient of discharge, the some amount of flow will be lost, okay, because of this piping restrictions and pressure drop and other frictions, other thing, and the value will be approximately 0.95 properly designed. But if you do not design this restriction part properly, then CD value will be higher. So CD value higher means higher energy loss will be there, so flow rate will not be will be lower. For example, I have one okay, left side you see, for example, I have one venturimeter smoothly designed like this, okay, I have another venturimeter maybe, or if this plate is created like this. So this flat section, this small hole is there, fluid will be passing through this one. This will be creating more restriction. So CD will be higher here. CD, let's say CD1, CD2. So CD2 will be more than CD1 actually. Okay. So if you do not design properly this venturimeter restriction section, then your flow pressure drop will be more, or flow rate will be lower as okay. But again, anyway, you are not destroying mass. So this is just practically how much flow rate you can get if you can create restriction because of narrowing down your pipe or tubing. Based on that, so we will try to solve one problem. Let's say we have one venturimeter. Okay, venturimeter, we have one venturimeter like this, restriction you are creating. Okay, you have one venturimeter installed like this, and I have one manometer here. Okay, manometer means it will having this one, this is section 1, this is section 2. Okay, and manometer section 1 pressure is higher, section 2 is lower. Okay, lower means like it will be like this. Normally this will be mercury or high density fluid, and because a pressure P1, P2, P1 is more than P2, so this column, you can see this column will be pushed down more. P1 is higher than P2. Okay, so this difference is called differential pressure. Okay, so in laboratory they will have like manometer like this. Manometer, the differential pressure will be noted down. From that differential pressure, if you get mercury column, then H rho g, using H rho g you can calculate how much pressure difference is created because of this narrow section. Okay, this is called throat section actually. Okay, throat section, you are creating very narrow necking down. With a diameter 10 centimeter inlet, so this is 10, D1 equals 10 is given, cm unit you have to note down, and 5 centimeter throat section. Okay, this is 5 cm, this is D2. The pressure difference between the inlet and outlet, P1 minus P2, this is given, P1 minus P2 equals 200 Pascal to 2000 Pascal. The fluid flowing through the venturimeter is water, so this is water actually. So to make your life easier, water means rho will be 1000 kg per meter cube. Look, it is already given also in this problem. If not given, then just you can assume 1000 or around some value, but it should be more realistic, not like 500 water density. Whatever you add salt, like salty water or something, maybe water density will be changing a little bit, but you cannot get like 500 or 1500. It will be 1000 or nearby, very closed. Okay, calculate the flow rate of water through this. So theoretical flow rate actually you have to calculate. Okay, because CD not given, so we are assuming this is theoretical flow rate. So to calculate this one, first you calculate area in Q equals A1 V1 equals A2 V2, because flow rate is not changing, although you are creating restriction, only velocity changing, area changing, right? So P1 minus P2 equals previous formula you can remember, rho by 2 into V2 square minus V1 square, right, from Bernoulli's equation. So there and A1 equals pi into pi d square by 4 or pi square, 0.1 divided by 2 square. Okay, why 0.1? Here d equals 10 centimeter, right? So 0.1 meter, so we are converting into meter, right? And this is diameter, so radius equals 0.1 divided by 2 meter. Okay, that I am using radius. Actually I should write pi r square equals, okay, r means radius, A2 also, then from here we get 0.00785 meter square. A2 we get 0.00196 meter square. So V1 coming A2 V2 by A1 equals 0.00196 divided by 0.00785. So it is giving into V2, it is giving 0.2497 V2. Okay, so unit will be same, meter per second. Okay, now P1 minus P2, P1 minus P2 equals rho by 2 V2 square minus V1 square implies 1000 divided by 2 V2 is V2 as it is I am keeping, minus V1 I already got 0.2497, 0.2497 V1 V2 square, this will be squared, sorry, this square and everything. Okay, so finally this is giving finally this is giving 0.00404 meter cube per second, but calculate flow rate. Okay, normally I ask in meter cube per hour. Okay, so meter cube per hour if you want to do, then 0.00404 into 3600, so it will be giving 14.54 meter cube per hour. Okay, so this is your answer. So I can change some data, you can modify the problem, even sometime I can give mercury column difference also in terms of Hg. So if I give Hg column difference instead of giving directly Pascal, so in that case what you have to do, you have to convert the H rho G, rho mercury you have to change and H you have to change, and then you have to calculate differential pressure. Now jet pump working principle. Okay, so jet pump you draw like similar to venturi meter. Actually you have one big pipe, then you are narrowing down, you are creating nozzle. Okay, then you are creating this section, you are creating this section, then this section. Okay, now this is section 1, this is section 2, this is section 3. Okay, so different sections I am creating. So here section 1 means upstream of nozzle, this is called nozzle. Okay, this is nozzle, this is nozzle. Okay, this is nozzle, this is nozzle, this is called throat section or mixing chamber. Mixing chamber, this is called diffuser. This section throat section, this section will be diffuser. So you can remember diffuser, I explained before also during your ESP system design. So diffuser means you are enlarging piping diameter, so velocity will be going down and pressure will be going up. Okay, so in diffuser what happens, velocity goes down, pressure goes up. Okay, mixing chamber throat section, what happens here, mixing of primary and secondary. Fluid happens. Okay, mixing of primary secondary fluid happens, and this mixing should be proper mixing. If improper mixing is there, then actually jet pump performance will be dropping. Okay, this is nozzle. So what happens in the nozzle section? Okay, in nozzle section pressure increases, velocity, nozzle section pressure decreases, velocity increases. Okay, in nozzle section. In mixing chamber these things happen, and this section, body section, actually secondary fluid enters. Okay, this is 3, 4, I'll put as a random name actually. I'm not following any rule now at this moment. So here suction of secondary fluid, suction, or this is called entrained fluid, or it is called produced fluid. Okay, here primary fluid, the different name of this fluid is there. Primary fluid, motive fluid, or power fluid. This is discharge, or delivery side, or discharge side, or discharge pressure, delivery pressure, they say. Okay, now what happens, you can remember this Venturi section, we created low diameter section so that their velocity will be increasing, pressure will be down. So this location, you see this nozzle section, velocity increased. Okay, so fluid will be passing through this, it will make like this. Okay, it will make streamline like this, and secondary fluid will be joining them. Okay, so there will be lots of mix up here, will be there. So mixing will be happening in throat section, that is called mixing chamber also. Okay, now how the pressure and pressure is varying. Okay, how this pressure and flow rate changing the nozzle actually. Straight nozzle is here. Now nozzle is going through one mixing chamber, the fluid is going through one mixing chamber. Then what happens if I take different section? So fluid velocity, pressure is going down, right? Pressure is going down here, then pressure will be almost fixed, then again pressure will be building up. Okay, this is pressure of power fluid. Okay, power fluid pressure initially going down at the nozzle. This is nozzle. Okay, this is nozzle section. Okay, nozzle section pressure will be going down. After nozzle also little bit down will be there, because normally when fluid is going through this nozzle, so actually the lowest cross section area will be created just after the nozzle, so that is called vena contracta area. The vena contracta area will have the lowest pressure, so their suction rate will be more. Okay, now entrained, this is pressure and power fluid. Okay, power fluid velocity, and velocity will be increasing again. Velocity, if I say velocity, the velocity increasing, then it will be almost constant, and again in diffuser section it will be dropping. Okay, power fluid. Okay, so this way velocity increasing, pressure dropping. Okay, what about flow rate? Flow rate not changing actually. So at nozzle flow rate is not changing, but when fluid entrainment happening, entrainment means from secondary fluid entering, so their total volume will be increasing. Okay, if entrainment happened here, so then total volume will be increasing. After suction, then there will be no change again. Fine. So a diffuser, fluid velocity reducing, pressure increasing. In nozzle, pressure decreasing, velocity increasing. Okay, cavitation. So this is a very important parameter we are learning from beginning, actually from beginning of the course, cavitation, whenever we are talking about fluid machinery, cavitation is one of the integral part of fluid machinery. When you are designing turbine, your pumps and compressors, playing with fluid, water, so cavitation will be one integral part. What happens in cavitation? Cavitation means, let's say some fluid is passing through this nozzle, it will pass through again one mixing chamber, right? So in mixing chamber, so normally fluid pressure will be very low. Okay, when pressure is low, water, if it becomes lower than the water vaporization pressure, okay, so vapor creates bubbles created. Okay, when pressure goes down, when it is trying to suck, pressure goes down, and when pressure is going down, bubbles will be created. Okay, so when bubbles created, now slowly it will try to increase pressure, because nearby jet or nearby nozzle entry pressure is low, then it got entered fluid, now again pressure will be increasing. When pressure increasing, what will happen? The bubbles will be collapsed. Collapsed bubbles. Okay, bubbles will be collapsed, or implosion, bubble implosion will be bubble implosion, bubbles implosion will be occurring. So when bubble implosion occurring, let's say this is surface, bubbles are imploding, so what will happen? Bubble imploding, so that high pressure pulse, very high pressure pulse, a high pressure pulse will hit the surface. Okay, high pressure pulse will be hitting the surface, fluid pressure actually, so that will be creating continuous alternating stress, on the metal surface. Okay, so when continuously alternating stress they are getting, bubble created, destroyed, created, destroyed, so the metal surface pitting will be there, so gradual erosion will be occurring. Okay, so erosion will be there, alternating stress will be there, so surface fatigue will be coming, then erosion of the surface, will be occurring. Okay, so when surface erosion occurring, so and if you have any sand or other particle, erosion rate will be higher. If you have higher other chemical also, again erosion rate plus chemical, the life will be more disastrous. So if you have pump, you have high speed machinery, this cavitation you have to consider. If you are not considering, then because of this erosion, after some time, like I already told, this jet pump normal life will be like 4 to 5 years, but if you have erosion and cavitation, then life will be lower. And jet pump is not having any moving part. So if you are an engineer, design engineer, every time you have to think, you have to reduce number of moving element in the system. So jet pump is the one system inside wellbore where there is no moving part. But if you see any sucker rod pump or PCP or ESP, they have lots of moving part. When moving part is there, life will be lower. But in this case, there is no moving part. One nozzle is there, diffuser is mixing chamber, diffuser, done. So because of this one, there is failure rate will be very low, lower than any other artificial lifting system. Okay, and if you give moving element, for example, hydraulic engine pump, the life will be lower. But in this case, life is definitely higher. But one main problem is that its efficiency is very low because of this nozzle. Okay, nozzle discharge, CD, some CD will be there, CD value will be there. There is losses is there, mixing chamber losses is there, suction chamber, diffuser, everywhere losses is there. So all the losses together, the efficiency will be 30 maximum. Yeah, we are doing some research in jet pump, so we got maximum 35% efficiency actually. Okay, maximum. So normally the books they are reporting 10 to 30% efficiency. Okay, so this is reliable. 10 to 30%. So 30% getting also will be difficult if you consider whole system actually.